Thank you so much for the nice introduction. The topic of my talk is quantum uncertainty principle for measurement with interventions. So let's start with the take-home message first. Okay, so every day we need to face some multiple choice question. And in classical world, if we remove the possibility to be A, we still need to figure out whether the answer should be B or C. But quantum mechanically, sometimes there exists example. When we remove the possibility to be answer A, uh, it cannot be B at the same time. So the answer can only be C. So that's a whole story we will talk about today. Okay, as a first part, we will focus on uncertainty principle. Nowadays, everyone is looking for quantum advantage. But right now, I'm interested in quantum disadvantage, a typical quantum disadvantage. That is a so-called uncertainty principle. In classical world, it is very easy to figure out. Given a football, we can find its position and momentum at the same time. But unfortunately, for a free particle, it's quite impossible due to Heisenberg uncertainty principle. And in the year 2019, 1927, Kienard gave the first mathematical formulation of Heisenberg uncertainty principle. That's a form, okay, everyone knows this. And the general form for bounded operator is given by Robertson in the year 1929. So this formula is bounded by the commutator between two different bounded operators. If we focus on position and momentum, then we can derive this colonic commutation relation, which covers the standard Heisenberg uncertainty relation for position and momentum. But in the information age, it is more suitable to choose Xiao entropy as a quantifier for uncertainty. Then we will have entropy uncertainty relation. So the first entropy uncertainty relation for general bounded operator is given by David Deutsch in the year 1983. And 4 years later, Krauss gave a conjecture that David Deutsch's result can be further improved. But this result has soon been, this conjecture has soon been proved by Mason and Wu Fink. Their result is more general. Actually, they focus on arbitrary range entropy with harmonic condition. That is 1 over alpha plus 1 over beta, which is equal to 2. And their mathematical detail based on Ray theorem from functional analysis. If you want to know the detail, you can check their original paper. And moreover, they have shown that for sequential uncertainty relation, the relation is equivalent to our conventional entropy uncertainty relation. So this is a well-known form. Here, the summation of entropy is never smaller than log 1 over C. And here C stands for the maximum overlap between two different measurements. But here now, all the uncertainty relation only focus on a single system. That means the system is isolated from any other system. But more generally, we can consider about the uncertainty principle in the principle of quantum memory. A typical example is considered about by EPR paper. When you check how Einstein considered about the reality of quantum mechanics, their example shows uncertainty can be reduced when quantum memory is there. And the general form is present in this Nature Physics paper. Now the Xiao entropy is replaced by conditional entropy, and the right-hand side contain an additional item, which is HA condition B. And this is the fundamental difference between classical world and the quantum world. Because for classical information theorem, this quantity will never be negative. But in quantum world, for example, like if you consider about maximum entangled state shared between measured system and quantum memory, this quantity can be negative. And then the uncertainty can be removed. For example, like you consider about mutually unbiased basis and think about the measured system is correlated with quantum memory, then there won't be any uncertainty. But you will ask a fundamental question. Why we choose entropy as a fundamental uncertainty measure? That should not be the case. Actually, if we give some fundamental rules, for example, like if you implement random relabeling, the uncertainty will not decrease, then this kind of rules will lead to the following modulation uncertainty relation. There's another rule, mixing random relabeling will increase the uncertainty. Then we will have this kind of modulation uncertainty relation. Definitely, modularization will not only play an important role in uncertainty, but it will also play a very important role in Nielsen theorem and in bezeling. But here, we will show Majorization uncertainty relation will lead to universal uncertainty relation. This is simple because here, if you implement any non-negative Su or concave function, you will derive some uncertainty relation. If this non-negative Su or concave function is Xiao entropy, you will recover the Xiao entropy uncertainty relation. So that's why we call it majorization uncertainty relation, universal uncertainty relation. Now, based on different classification, we will have different forms of uncertainty relation, and based on whether it has memory or not, we will have different forms. If you want to know the detail, there are lots of reference for you. And moreover, till now, uncertainty relation is still a very important research area because it has so many applications ranging from witnessing quantum correlation to cryptography until engineering problem. And here I want to highlight, for example, like we can further apply uncertainty relation to formulate the band for no programming theorem. No programming theorem like is formulated by Michael Nielsen and Chuang, and they say there does not exist a universal quantum programmer. But actually, the band can also be formulated by uncertainty relation. We will submit this paper to archive, hope within this year, hopefully. Okay, till now, all the uncertainty relation considered now is passive measurement. That means when we try to learn some physical property of a quantum system, we simply let the system evolve before observation. But definitely, this is not the most powerful way of learning. The most powerful way of learning should contain interventions. For examples, like even for toddlers who want to gain information from its environment, she will not stay until she can perform some measurement, but she will do some intervention like she throws some stone to the lake surface and see the result. And based on this result, she will do it again to understand the relation between her action and the surface lake surface. To formulate this kind of simple idea into quantum world, we can think about the general interactive measurement. Let's start with some simple example. So the first one is like, we are interested in quantum dynamic, not only focus on one time points, but multiple time points. Initially, we prepare some quantum state, and then in the future, between system B and system C, we will have the future evolution of quantum channel psi. Now, in order to get information from the system, which is in color blue, we implement some quantum instrument between system A and system B. Then we can read out classical output. And then we implement PLVM, general PLVM to system C. Now, based on this classical output, we can formulate the so-called pseudo-density operator. It's very important and so many applications. And more generally, this kind of mathematical technique can also be used in quantum causal inference. But more generally, no system is isolated from its environment. So we cannot assume the initial state has no influence on its future. So maybe the initial state rho is replaced by a bipartite system, and it is connected with its future evolution, like psi shown here. And moreover, our intervention can be replaced by some quantum channel shared between A and B. Moreover, we can prepare some reference system R. And after all the intervention is done, we can implement a joint measurement between system of interest C and reference system C, R. More generally, when we have a non-Markovian quantum dynamic colored in blue, we can also implement the following interactive measurement TX. It includes finite range of quantum channel, and after all the intervention is done, we implement a joint PLVM between the system of interest and the ancillary system R. That's the most general form of interactive measurement. And here X denotes the measurement outcome. Interactive measurement is very important. The motivation comes from at least two parts. The first one is like, previously we investigate uncertainty relation for quantum state, but we have never asked the following question. Does uncertainty relation for quantum state ever exist? Because quantum state, the fixed time does not exist. The system will always evolve due to the Hamiltonian. So at least we should focus on uncertainty relation for quantum process. If you are interested, we have already introduced uncertainty principle for quantum processes. Another reason is like so many interesting protocol include quantum illumination, quantum enhanced agent, and the open quantum system forms a non-Markovian quantum dynamic. So the way of getting information from them forms interactive measurement. Now let's try to formulate an uncertainty relation for interactive measurement as a following guessing game. We have assumed we have two agents, Alice and Bob. Here, Alice has two interactive measurements, T1 and T2. Bob can prepare arbitrary quantum dynamic and interact with Alice. Bob knows this interactive measurement T1 and T2. Right now, we assume Bob have K bets and can put to the table. For example, like if Bob has two bets and he put 1, 2, 2, 1 table, this position, then that means Bob guess either Alice is implement T1 measurement and getting outcome 2, or implementing T2 interactive measurement and obtaining outcome 1. Whenever one of them is correct, we say Bob wins the game. Now try to maximize all his winning probability. We will derive the following majorization uncertainty relation. Here, 1 over half means Alice will implement interactive measurement with equal probability, and all the maximum winning probability will form this the bound for uncertainty relation with this vector form. And moreover, if we arrange all the probability distribution with non-increasing order, then the probability simplex becomes a majorization lattice, and this majorization forms a partial order. And because it forms a complete majorization lattice, we can always find the optimal bound. In order to gain this bound, we should implement a technical called flatlist process from this IEEE paper. And moreover, because entropy can change the order, by applying Xiao entropy directly, we can obtain the entropy uncertainty relation for interactive measurement. Now let's move on to the second part of this work, causal inference, and try to show how to build a connection between uncertainty relation and causal inference. A new research area plays an important role in healthcare and AI. Due to common cause principle, we know given two events x and y, their causality can only be three cases. The first one is x directly causes y. This is so-called direct cause. On another hand, given two events x and y, they may be correlated, but there's no direct cause shared between them. But there's a common cause for them. So this is second causal structure, common cause. More generally, there will be a mixture between direct cause and common cause. Quantum mechanically, there are some examples to show the causal diagram. For example, like the first row. So here, we prepare some initial state and implement quantum channel shared between system B and system C. Now it is easy to imagine. We do something between system A and system B. Then this event X will be the direct cause of event Y after system C. On another hand, we can prepare some bipartite entangled state shared between system A and system C and trace out system B. Now the event X and event Y will have a common cause. But more generally, we can implement some superchannel. This is a special case of a superchannel called causal map. For the pre-processing, it does not have any input, so that's why it's a special case. It shows a mixture between direct cause and common cause. In order to figure out its causality, we introduce two families of interactive measurement. The first family is TCC. We call it common cause indicator. And here, we assume the quantum dynamic inside this blue box has rank 1. So here, rank 1 means it's Xiao operator where it has rank 1. Now, if we implement common cause indicator and obtain measurement account with certainty, then we can confirm the quantum dynamic will have a causality of common cause. Similarly, we have also introduced the interactive measurement of direct cause indicator. If the measurement outcome happens with certainty, we can conclude the quantum dynamic can only be a direct cause. Now we are trying to build a trade-off between these two different families of interactive measurement. For previous uncertainty relation, they only focus on trade-off between two different observables. But here, we focus on the trade-off between two families of interactive measurement. And here, we are only interested in the optimization value. So we can always try to observe the unitary inside the blue box. So here, I want to make a remark. We do not determine U1, U2, U3, U4. They are arbitrary unitary gate. So that's why they form two families of interactive measurement. And starting from A1, B1, finally we can derive A3, B5 and figure out the fundamental trade-off between them. Now I will further share how to use this kind of causal uncertainty relation to figure out the causality of quantum dynamics. Let's focus on the quantum circuit shown here. The initial state is the maximum entangled state shared between system A and some quantum memory. And here, Z and X denotes rotation along Z and X directions. The blue surface shows real uncertainty, and the plane shows our band. So it is easy to figure out that our band is tight in this sense. And moreover, the individual uncertainty is shown in figure 3. Now let's figure out how to use uncertainty relation to do causal inference. Let's move on to this quantum circuit. We already know that HTDC is equal to 0 if and only if the quantum dynamic has a causality of Dirac cause. Similarly, HTCC is equal to 0 if and only if its quantum dynamic shows a common cause. And here, our causal uncertainty relation becomes HTDC plus HCC is never smaller than 2, and 2 is a non-trivial bound. Now, assume we implement some measurement and gain the uncertainty of 0.5, then we can conclude it won't be Dirac cause. But at the same time, we know HTCC is greater than 2 minus HTDC, so it's 1.5. And hence, we can conclude that quantum dynamic cannot be a common cause. In this sense, the quantum dynamic can only be a mixture of Dirac cause and common cause. That's why uncertainty relation can be used to do causal inference. Moreover, for this kind of quantum circuit, we show always uncertainty in a right column. And here you can see, except the dots, we can figure out always causality. Because for most of the case, the causality should be a mixture of Dirac cause and common cause. And if you use tomography to do causal inference, it will require d power 3 different interactive measurement. If you use a pseudo-density operator, then it will require d power 2 different interactive measurement. But here, if you use causal uncertainty relation, a single interactive measurement is enough. Here, tomography does not guarantee you can really do causal inference. I can give you an example. For example, like given a density matrix of a bipartite quantum state, like rho AB, can you figure out whether it's entangled or not? So you cannot. Similar situation applies here. Now let's come back to take-home message again. So classically, if we remove the possibility to be Dirac cause between two different events, we still need to figure out whether the answer should be common cause or mixture between Dirac cause and common cause. So it's a hard question. But quantum mechanically, if we remove the possibility to be Dirac cause, then causal uncertainty relation will help us remove the possibility to be common cause too. So the answer can only be mixture of Dirac cause and common cause. So now let's make a conclusion. In quantum foundation, there's a typical quantum disadvantage called uncertainty relation, and there's a new research area called causal inference. We use uncertainty relation to build a connection between them called causal uncertainty relation. This causal uncertainty relation transforms the original quantum disadvantage into quantum advantage. If you want to know the story, you can find our paper here. But if you want to find all the mathematical details, we also offer 47 pages of supplementary material. So our paper is definitely non-expert friendly, but our supplementary material is also experts unfriendly. Thank you so much.
Yeah, thank you very much for the great talk. So if there are any questions, please approach the mic. You can also line up and then it's faster.
Thank you for the nice talk. So you had this uncertainty constant C of T1, T2. How does it look like, and is it hard to compute for given T1 and T2?
It's not hard to compute, actually, because we can use STP to formulate the so-called majorization acceleration first, and then using entropy, we can directly transform the majorization acceleration into entropic form. So not so hard. We just need to calculate the maximum winning probability for our guessing game, shown here. Yes. So we just need to calculate the maximum winning probability, and we can formulate a so-called VT1, T2. This is a vector form bound, and it only depends on interactive measurement T1 and T2, does not depend on quantum dynamic. So it captures the incomparability shared between interactive measurement T1 and T2. And moreover, it's optimal. Our result for modularization is optimal, but does not guarantee it's optimal for entropies. Yeah.
Right. Thanks for this interesting talk. I'm wondering if you have looked into using your uncertainty principle to bound the set of correlations that people studies in a Bell scenario. Does it give rise to tight bound of the boundary of the quantum sense? Have you thought about that?
Thank you so much for your question. I think it's a very good question. And in the year 2010, there's a work describing the connection between Bell non-locality and fine-grained acceleration by Jonathan and Stephen Warner. And definitely, we can extend this kind of idea to temporal Bell non-locality. I'm also thinking about extending EPS steering from state case to bipartite channel, and it is strongly related with uncertain relation in the principle of quantum memory, but for bipartite channels, not for state. So this kind of work still under preparation. I'm working on them.
Right. Thanks.
Hi. Thank you very much for maybe the most entertaining and and interesting talk of the whole conference for me. I wanted to
Thank
ask
you so much. Thank you.
I wanted to ask you what is there like a general bound? So I want to understand like you know, you have this uncertainty relation is a general formula for everything. Is there something that you can say about from causal inference that's equally general? Like, is there some kind of inequality that you have for causal inference that reproduces uncertainty relations?
Very good question. Here we only focus on like two events, so we can see a clear connection between causal inference and uncertain relation.
Yeah.
But for more general cases, causal inference focus on the connection between five different events. So it's much more complicated. We have thought about that, but do not have any result yet. But we will think about that, try to get some result. Because recently I'm also thinking about a sequential acceleration. That okay, let me show a picture. So for the first row, you can see the protocol for pseudo-density operator. You can imagine this is a sequential acceleration because you implement measurement between system A, B, and then measurement on system C. What will happen if we replace a quantum channel appeared in the last row with all POVM, and how to figure out the uncertainty between all this measurement? This is a very interesting topic, and I think this is strongly correlated with general causal inference, but I still do not derive any result yet. Thank you for your question. Maybe we can discuss more.
Yeah, thank you very much.
Thank
And one last follow-up. Where did you make your figures?
What?
Your cyberpunk figures. How, did you make them yourself?
Oh no, no. by using AI. Yeah.
AI. Okay, amazing.
Yeah.
Hey, thank you for the nice talk. So I was wondering about this sequential uncertainty relation that you show. So there, basically, everything that you're considering is like a fixed temporal order in the sense that like there are these kind of quantum comb with a fixed
Yes.
direction of time. And have you thought about the non-causally ordered scenario? So
Yeah, very good question. Yeah, definitely. Because my background is math, so when I thought about some formula, I was thinking about all possibility in quantum theorem or even beyond causality. But the problem is like, can we find a good motivation for uncertain relation with the indefinite causal order? I didn't solve this question, so
okay,
that's
but
why.
like so motivation aside,
Yes.
I would just be interested. Like, is there any result?
If I can find
for
any
uncertain
application, I will write down the paper immediately.
Okay.
Thank you for your nice question.
Do we have more questions? If not, let's thanks again for this great talk.
Thank you.